All right, so we're going to take this checkerboard and we're going to put one checker on the first square. And then we're going to put two checkers on the next square. And then 4, and then 8, and then 16, and so on. So we have our checkerboard here. We have a pile of checkers. We put 1 on the first square, 2 on the second square, 4 on the third square, 8, 16, and so on. And we're going to do that on this whole checkerboard that has 64 squares. If we do that, continuing this pattern, by the time we get to the last square of the checkerboard, which would be the 64th square, we will have enough checkers stacked up to reach the nearest star. She said, wait a minute. If the sun, if you count the sun as the nearest star, that's still 93 million miles away. We're talking about putting checkers on checkerboard. You can't possibly get that many checkers. I said, well, let's figure it out. Let's see. So if we look at this pattern, could you all continue it? What's happening? We're multiplying by 2, right? So this is what we call a geometric sequence. And you can write this down later. You don't need to write it down now. I want you really listening now. This is a geometric sequence. Geometric sequence means we build it by multiplying by some number. In this case, it's 2. It could be a different number. But we multiply, multiply, multiply. They tend to grow pretty fast. Now, if we analyze our terms here, the first term, and I'm going to go ahead and use sequence notation. Do not be confused. A sub 1 just means first term is 1. Now, the second term, I'm using sequence notation, A sub 2. The second term is the first term times 2. That's what you said. What's the third term? It's this one times another 2. And then this one is that one times another 2. Right? So what's happening here is, if you look at this carefully, you'll see there's a relationship between the term number and how many 2's we multiply by. The fifth term would be that one with another 2. So wouldn't it be 1 times 2 to the 4th?
Yes.
So see the relationship between the term number and the number of 2's you have? So what would the 10th term be? What would the 10th term be? It'd be 1 times 2 to the 9. Well, we're interested in the 64th square of the checkerboard. So the 64th term will be 1 times 2 to the 63rd. Okay, if you brought a calculator today, please get it out. If you didn't bring a calculator today, you really, really, really need to start bringing your calculator. You're going to find out in the work with you today, guys. If you have to do all this by hand, it is just going to take you weeks. Bring a calculator. You don't have to have one today. You don't have to have one, but you need to start bringing it. Okay, so somebody with a calculator. Does everybody know how to type in 2 to the 63rd? 2 raise that little caret deal to the 63rd? What'd you come up with? 9.223 times 10 to the, there should be an E in there. 18. All right, gang. That, my friends, is a big, big number. Keep in mind, a million is 10 to the 6th. A billion is 10 to the 9th. A trillion is 10 to the 12th. This thing is bigger than that, right? I don't know what that is, but there's some word for that probably. That's huge. But that isn't a distance. That's how many checkers there are. All right? So here is about an inch. How many checkers can I pile on top of each other to make that distance, would you say?
5.
5? That seems kind of high to me. Maybe really skinny checkers.
3.
Maybe 3. I think about 3. It doesn't matter, we can use 5, but I think 3 is a more reasonable number. So let's take this number and divide by 3. So go ahead on your calculators, hit divided by 3. And what does it say?
3.07.
Times 10 to the 18th?
Yes.
Okay, now that's how many inches you have. So now we're getting a distance. You have 3 point whatever times 10 to the 18th inches. Now let's divide that by 12. What will this tell me if I divide it by 12? How many feet? So how many feet do we have? Times 10 to the 17. We still have a big number. So now, one more thing, let's divide it by 5,280, because that will tell me how many miles of checkers I have. What is it?
4.8
Times 10 to the 13. Kids, that's miles. Now remember, 10 to the 6th is millions. 10 to the 9th is billions. 10 to the 12th is trillions. This is more than that, right? That's how many miles of checkers would be on that last square. Isn't that amazing? Just amazing. Izzy?
So you divided by, I just was like, I got lost for a second. Like right when you divided by 3, like I got confused. Why are we dividing by 3?
Because we decided there were about 3 checkers per inch.
Okay.
So I don't know how many inches.
And then 12.
To how to find feet.
And then where did you get 5,282?
That's how many feet there are in a mile. So to figure out how many miles, right? All right, pretty cool story. Phenomenal. One more quick story along these same lines. Back in my very early days, you know how it is. You've all had a new teacher before, right? And sometimes you try to get away with stuff with new teachers that you don't try to get away with other teachers. And I had kind of an ornery geometry class, great kids, and they've all grown up, and I still see some of them from time to time. But there was a sophomore boy in this class who was a very good wrestler. Cathedral's always had a proud wrestling tradition, or at least as long as I've been here. And this kid was a really good wrestler. And in the old days, we could do things that we can't do now. So when a kid was misbehaving in class, I would sometimes like never whipped anybody, but I would draw a circle on the board over there or something and say, put your nose in it and stand there for 10 minutes or something. So the kid didn't have to stand there like this for 10 minutes. Or give me 15 push-ups right now. Something like that. Well, this particular young man was very good wrestler, very proud of his physique. Nice kid, but very ornery. And he would deliberately like do stuff to aggravate me so that I would say, do 15 push-ups, and then he'd be like showing off, one-handed, and clapping, crazy stuff. So I said, okay, we're done. We're gonna make a deal. This kid did not want to be in school. He was only a sophomore, so he had to come to school. But he didn't want to be in school. He didn't want to do geometry. He didn't like me. I mean, it was just a bad scene. So I said, okay, let's make a deal. And we actually made this deal. We went to the dean's office. We had a dean at the time. We went to the dean's office. His mom signed off on it. And this was the deal. You must come to class. That's state law. You have to be in school. But you do not have to take any tests, take any notes, do anything. It's got to be quiet. You can't be like messing around in class, but you got to be quiet and respectful. But you have no geometry obligations whatsoever, as long as you can continue to do this. You're going to do 1 push-up today. You're going to do 2 push-ups tomorrow. You're going to do 4 the next day, 8 the next day, 16 the next day, and so on. And as long as you can continue that, you don't have to do any geometry at all. Oh, now wait a minute. You should be thinking, Mrs. Ford, that was mean. Because it doesn't take very long. I mean, even our best athletes, it doesn't take very long until you just can't do it anymore. For one thing, there isn't enough time. Even if you could do, 80,000 push-ups, there isn't enough time in the day to do it. And then next day, you're doing 160,000 push-ups. And so he went on for a few days. He made it for a few days. But then obviously he came to a point where he couldn't do it anymore. And then he was good the rest of the year. It worked out great. The little note I want to make here is don't make a deal with Mrs. Ford because she's not very nice. Anyway, enough stories. Here are some notes. Let's take some notes here. Well, we went out, everything was
I was gonna say, where do we send that? Right.
I will tell you though that that young lady that came in with the check problem, you probably know her son. Did any of you know Isaac Michael? He's a junior. His mom is the one that came in with the checker problem.
Just gonna get an A this semester. Hoping for more confidence, but that's
Do I want to get an A this semester? Yes.
What did you just say, Henry?
Oh, Lord.
I'm wondering why you want to get a B. Let's want to get an A.
No, I said I want to. My man asked me, am I?
Get an A.
I would like to roll dry.
All right, here we go. Izzy showed up, Hunter is still on. Seriously.
That's what I'll do.
All right. Yep, the new semester starts now. The A's start right now, so let's start getting them going. All right. For each sequence, find the next 2 terms and then which sequences are geometric. Now remember, geometric means that you get from term to term by multiplying by some number. Now when you look at sequence A, I have no doubt you can fill that in. What are the next 2 terms? 10 and 12. Everybody's got that. But how are you doing that? Adding 2. And adding 2 is fine, but it's not geometric. So A is not a geometric sequence. There is a pattern, you can keep going, but it's not geometric. All right, what about B?
81.
The next 2 terms are 81 and 243. Now again, if you're sitting there with a calculator, you're typing in times 3 times 3, right? If you're not, you're working it out. Bring the calculators. All right, is B geometric then? Yes. And the common ratio, might as well get used to this word too. The common ratio is 3. The common ratio is simply the number that we multiply by. So in sequence B, we keep multiplying by 3. That is called the common ratio. C is wild and wacky. If you get C, I will clap for you. It is a tricky one. Mikey?
So is it you add 0, then 1, then 2, then 3?
Well, let's see. So you say I add 0, I add 1.
And then 2, then 3.
Wait, what did I add here?
You add 3, then
Wouldn't that be adding another 1?
wait, no, not that.
And then this would be 2, right?
Yeah.
That's kind of crazy the way that works. I don't know.
And then you add 3, then 5.
So you're saying add 3, so the next one would be 8, and then 12. Is that what you said? Okay, now, Sam?
I thought maybe like the two numbers add together. So like 1 plus 1 is 2, and then 2 plus 3 is 5.
There's your clap, Sam. Good job. So Sam says, Mikey, I think you were kind of close. You're onto something there. But like Sam said, what's really happening is you add these two to get the next one. And then you add these two to get the next one, and so on. So to get the term after this, Mikey, you were right, it's 8, because it's 3 plus 5. But then the next one would be 13, because you have to add 5 and 8. And then the next one, if we had to keep going, would be 21. And 34, and so on. This sequence is so famous, it has its own name. Make a little note next to it. It's the Fibonacci sequence. And you guys that think all math is just made up so that you can be miserable, there are actually whole books written about the Fibonacci sequence because it actually occurs in nature. The next time you're out tromping around the woods, pick up a pine cone. And if you count, you know, pine cones have, you know, they have a Christmas tree shape, they have these kernels. If there are 13 kernels in the bottom level, the one above it will have 8. The one above that will have 5.
Does that happen in trees too?
It happens in trees.
Like the ring? Or is that
Oh,
just
I
the
don't know.
age?
I have a great question. Google it. It happens in sunflowers. You know how the seeds are in a sunflower? It happens in honeycombs. You know what a honeycomb, beehive honeycomb looks like? So when you are bored and you need some stimulation, Google Fibonacci and there's a ton of information about it. But it's this sequence right here. Okay? All right. Is it geometric? All right, D. What's going on in D?
You're
Adding
adding 1.5.
1.5. So the two terms we have to fill in would be 3 and 4.5. Is it geometric? No. No. E is another tricky one. What would you say, Anthony? What do you mean squared? So 1 squared, 2 squared, 3 squared, 4 squared. So 25 and 36 are the next terms. Everybody see that? Sean? Everybody see that? Okay, good. Is it geometric? No. Geometric means that I would multiply by the same number to get from term to term. So I multiply by 4, then I would have to multiply by another 4 and another 4. That's not what's happening. This is not geometric. There's a sequence, it's a pattern, but it's not geometric. F. Multiply by 3. Does everybody see in F we are multiplying by 3? So the next term, oh, I need a calculator. 405 and 1,215. See how handy those calculators are? Is it geometric?
Yes.
Yes, and its common ratio is 3. How about G? Multiply by 2. So the next terms would be 32 and 64. Is it geometric? Yes. And the ratio is 2. Very good. Now H, don't be confused by the negatives. You can do this. What's happening in H?
Times by -3.
We're timesing by -3. So the next two terms would be -81 and +243. What's our ratio? -3. Yep. Your ratio can be negative. You're allowed to multiply by a negative number. Okay, I see some lanyardless people that don't have stickers.
Oh, that sucks.
Lanyard? Hurry back. Aren't you that lanyard's supposed to be electric? All right, number 2 says find the missing terms of the geometric sequence. So these are geometric, and you have to fill in all of the blanks. So who's got a thought? Anybody have a thought on that, Mikey? Dividing by 2. Now let's talk about that for a minute. First of all, is he right? Does it appear that we're dividing by 2? Now, Mrs. Ford just told you this was a geometric sequence. And I said geometric sequences were sequences where you get from term to term by multiplying. So what am I multiplying by? 1/2. So the ratio is 1/2. Now, it is perfectly okay to think about it as dividing by 2, as long as you recognize it's still geometric, because dividing by 2 is the same as timesing by 1/2. And with the fractions, it might be easier to multiply by 1/2, right? So if we multiply by 1/2, what would this term be? I'm multiplying by 1/2, guys. You can do this. -3/8 and -3/16. Perfect. Now we're getting wild and wacky. We got to go the other direction. What am I going to do to fill in these blanks here at the beginning?
Divide by 1/2.
Dividing by 1/2, which is the same as multiplying by 2. So this one would be -12 and -24. Does that make sense to everyone? What about this one?
Times 5.
What's happening here? What's our ratio? Times 5. Now, this one I'm only going backwards on. So timesing by 5 propels me forward. What's going to bring me back? Dividing by 5, right? So 1/5, 1/25, very good. 1/125, and oh my goodness, 1/625. Everybody okay with that? We multiplied by 5 to go forward, so we had to divide by 5 to go backwards. All right, now we got a sequence 2, 6, 18, and 54. And you need to, number 1, find the common ratio. That should be easy for you. What's the common ratio? 3. How do we know it's 3? Because that's what we're multiplying by. So that's 3. Now we need to find the 10th term. Now there are a couple of ways you can handle this. A sub 10 means 10th term. Okay, that means the 10th term. could you just start with your calculator, hitting times 3, times 3, times 3, times 3 till you got to the 10th one? That will work. It will work every time. The problem with it is, it's not bad if it's the 10th term, but what if it's the 100th term? It takes forever, right? And then you lose track of stuff, you miscount, whatever, it ends up being a mess. So let's think back a minute to our checker problem. Does anybody remember how we found the 64th square? How did we do that, Lauren?
2 times 1 times 2
To the 63rd, that's right. Because we noticed, Lauren, that there was a relationship between the term we are looking for and the number of 2's that we had. So can we use that idea on this problem? The 10th term isn't going to be a 1 here. 1 was our first box, right, of checkers. Our first term is actually 2, so we're going to have to start with 2. And then we're going to multiply it by 3 to the what? 9. Beautiful. Why 3? Where did 3 come from? That was my ratio. Whatever my ratio is, that's what I multiply by. Now, I want you to type, those of you that have calculators, I want you to type this in. And if you type it in exactly the way I wrote it, you will get the right answer, which is 39,366. So if you're not getting that, you're not typing it in right. Okay, so one more time before we turn the page, go on to the next problem. How did we find the 10th term? We took our starting term and we multiplied it by our ratio to the 9th. All right, let's look at the next one.
How do you know it's always a 9?
If this is a 10, this will be a 9.
So it's one more. Or one less one.
This number is 1 less than this. So if this had been a 15, then that would be a 14. Yep. Okay. All right, so let's look at the next one here. First thing you have to do is figure out your ratio. So who can tell me what the ratio of this is? Hey, Sean and Shiloh, if I have to separate you, I will. I really don't want to. We're seniors in high school, but I need you to pay attention. Okay? My ratio is -2. Very good. Everybody get that? Now, once again, we want the 10th term. There's nothing special about the 10th term. Just that's the one we're asking for. How do we find the 10th term? What do we start with? The first term. So we're going to start with the first term. And then we're going to multiply it by what? -2 to the 9th power. We start with the first term, and then we multiply it by the ratio to the 1 less power. Mathematically, that looks like this. I don't want to confuse anybody with a bunch of letters, but that's what you're doing. To find a term, you start with the first term and multiply it by the ratio to 1 less. So, did you type this one in?
Yeah.
All right, let me type it in. I'm low on batteries. This is not good. I got 1536. Good? Right, how about the next one? What's the ratio? 1/2. Now, especially where you're using your calculator, 1/2 is fine, but feel free to use 0.5 if that's easier for you. 1/2 is fine. Your ratio is 1/2 or 0.5, whichever one's easiest for you to use. Does everybody understand that? Now, we want the 10th term. So what is our formula? What does our pattern tell us we do? 16 times 1/2 to the 9th. Type it in. Now, some of you will get a decimal and some of you will get a fraction. It doesn't matter. Both answers are perfectly okay. Decimally, it's 0.03125. Fractionally, it's 1/32. So either one of those answers is perfectly okay. Just sort of depends on how you have things set up on your calculator. All right? Everybody doing okay? Now let's look at the next problem, because this is a blast from the past, sort of. This is a mixture of the old and the new. Sean is starting a new job. He earns $36,000 in his first year, and he gets a 4% raise every year. How much will he earn in his 6th year? Now wait a minute. Who's got some thoughts on this?
What are we gonna do?
Izzy,
If he earns, well, yeah, if he earns 36,000 in his first year, and then it raises 4% every year after that, then multiply it by 0.04.
almost. She's right that it's a multiply problem. But think of our tax and discount situations, guys. We're going to multiply by 1.04, right?
Yeah.
Because his salary is going up. So we're going to start with 36,000, and we're going to multiply by 1.04. Now, if you do that, you can type that in. What does that tell you? That tells you how much money he makes next year,
Yeah.
right? We don't want to know next year, though. We want to know in 6 years or something. So what could we do?
Well, the ratio is 1.04.
Just keep multiplying by 1.04. You could just keep doing that. Or you could stop and think a minute. Wait a minute. Isn't this a geometric sequence? Aren't I multiplying by 1.04? So if I want to know the 6th year, how do I find the 6th year?
The formula.
I take the first year and multiply it by 1.04 to the 5th power. Now, 2 things. First of all, I want to reinforce that just like on your semester exam, when we did the tax and the discount and all that, when we're talking about increasing or decreasing by a percentage, we never use the percentage. We either do 1 plus the percent if we're growing, or 1 minus the percent if we are shrinking. Do you remember that? So that's why we're using 1.04. All right, type it in, round it off to the nearest cent because it's a money problem. And it looks like he's going to be making $43,799.50. Is he?
So if we were decreasing, would we be multiplying by -0.96?
Not negative.
Or 0.96?
Yep. And we're going to do that in our next problem, is he? Hang on to that. We'll do that in our next one. Everybody type it in and get this number. All right, let's do the next one. Kyla's expenses decrease 11% a year. Decrease 11%. What are we going to be multiplying by if we are decreasing by 11%? 0.89. Where did that come from? 100 minus 11. We're going down. We want to know her expenses in the 4th year. So what do? We start with 1, 2, 3, 4. We multiply by 0.89 to the what power? Third. And that's it. Guys, isn't this easy? This is so easy. 1, 2, 3, 4. 0.89. Third. I got 869.93. Is that right? So one more time. If we're talking about things growing by a percentage or shrinking by a percentage, don't multiply by the percentage. You either do 1 plus the percent or 1 minus the percent. All right, this next one is wild and wacky. I need your help. What is going through your mind when it says the 3rd term is 63 and the 5th term is 567? What is going through your mind, Anthony?
I multiplied by 3 for 63, and I got 189 to multiply 189 times 3.
Okay, now you're right on target. Perfect, beautiful. But why did you choose 3? How did you get to that point?
Because I was trying to find a number in the middle between 63 and 567.
And you figured out that if you took 63 times 9, you got this number? Okay, so here's what I want you to do. I'm going to show you the math way to do this problem, but it's going to confuse the heck out of most of you, so I want you to just think about it for a minute. Basically, you've been given these 2 numbers. You need to figure out how you can get from 63 to 567. Now, I've told you that it's geometric, so you know multiplication is involved. So what times 63 would give you 567? 9. You can figure that out on your calculator, 9. Now, timesing by 9 would take you straight from here to here. You have to do an intermediate step. So instead of timesing by 9, you're going to multiply by 3 and then another 3. Do you understand that? So if we times this by 3, we get 189. And then if we times it by another 3, we get 567. So we started by figuring out what it took to get the big leap, right? So if it had taken 16, then I would have multiplied by 4 and 4, right? Okay, but I need to know this number. How do you know it's 7? Because you know the ratio is 3, so we're going to back up. So this has to be 21, and that has to be 7. Beautifully done. Now I'm going to show you the mathematical way to do it, but you do not have to do it. That is exactly right. That is fine. That is perfect. But if you need a math way to do it, it would be this. And the reason it would be this is because that last term right there, at this point, these are the only terms I know. I don't even know that one. So the last one equals the first one I know times some number to the second. Now, why is it to the second? Well, how many terms are up here? 3. And this is always 1 less. So since there's 3 terms, that's got to be a 2. So I'll divide by 63 and take the square root, and r equals 3. That is the math. If that's confusing to you, don't do it. Figure it out in your head the way we did. All right, now, hold on to your hats because the fun is really going to begin now. Woo, I know.
We're having fun already.
Part 6. Number 1, you all should be able to do. So take a second and see if you can do part 1. We've already done something like this. It's a repeat problem. I think you can figure it out. Do we know what the word depreciates means? Decreases in value. So if we're depreciating 8%, what are we going to multiply by? 0.92. Very good, Marco. 0.92. So 5 years. I hope what you're doing is taking 25,000 times 0.92 to the 4th. Is that what you're doing? That's what you should be doing. So the value of that combine is 17,909.82. Is that what you got? Now it's this next one that is interesting. Would you agree that if we keep going, that value of that combine is just going to keep going down, 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 down? And at some point, it's going to be worth half of what it was before. At some point, it's going to be worth a third of what it was. It's just going to keep going down. If we want to know when it's going to be worth half, could we just keep multiplying by more 0.92s until we finally get to where we want to get to?
Yeah, there's an easier way to do it.
Do you think when we do that, though, that we will ever get a value that is exactly half? No, it's going to come out with weird things like this, right, Mikey?
What, so you just have like stick in the graphing calculator then?
So you have what?
Do you just stick in the graphing calculator then?
Oh, certainly graphically we could absolutely do that. That is a great thought. And we might, if we have time, try that tomorrow. I want to get through how we're going to do it without the graphing calculator. But yeah, that's a great thought. Remind me of that tomorrow. And when everybody do I see you tomorrow? Okay. When everybody has a calculator tomorrow, we'll go through that. All right, so let me get back on track here. Very good thought, though. We could just keep multiplying by more 0.92s, but we're never going to hit this exactly. So, oh, Brandon?
Why would you just put in half for the A5 and then put in X for the exponent?
Okay, now, yes. So what Brendan said is, you need to take your hat off, honey. What Brendan said is, we want this number to be 12.5. We want to figure out what we have to multiply, how many times we have to multiply this to make that number come out to be 12.5. Would you agree?
Yes.
Now, I don't want to confuse you. Why is that n minus 1?
So that's how it is in the formula.
Because it's always 1 less than the term number, right? That's just the way it is. All right, how do I solve this equation?
Wait, why is it 1 less than
What? Hey, Izzy, go back to the checker problem. When we wanted to find the 64th term, it was 1 times 2 to the 63rd.
Got it.
The exponent is 1 less, always. Now, how would I solve this? Come on, somebody knows.
Well, you need to get rid of the
You need to get
2500.
rid of this first.
So divide by that.
So we're gonna divide by that.
Make it a fraction on the other side.
So this is just going to be 0.5. Please don't be confused by that. I am dividing by 25,000. Isn't this number half of 25,000?
So just be a fraction.
Now, this is called an exponential equation. This is an exponential. Remember one of your BFFs was this?
Yep.
That was exponential because the variable is the exponent. Isn't our variable the exponent? So this is a version of an exponential. So tomorrow when we graph this, if Mikey reminds me, this is going to be an exponential curve.
Yep.
Okay? Now, to solve an exponential curve, you have to make this number not an exponent anymore.
Make it 1.
So here's what I want you to write down. Hold on to your hats. Everybody's got this equation. In the front of each side,
Don't make it 0.
I want you to write log. We are taking the logarithm of both sides. We are not going to spend weeks learning the properties of logarithms and all that. We're going to use logarithms. And this is how we use them. Take the logarithm of both sides. The best magical, mystical, wonderful thing is the minute you do that, this comes out in front. So now your equation says log 0.5 equals n minus 1 log 0.2, not 0.92. This is day 1. Do not panic. I want you to write it down. Write it down. So the first thing we did was put log in front of both sides. Then the exponent gets pulled out in front. Now I want you to divide both sides by log 0.92. So this is going to cancel. You're going to have n minus 1 equals. When you type this in, caution. If you hit log on your calculator, does it automatically put a parentheses in for you? You must close that after the number. So log 0.5, close parentheses, divided by log 0.92, close parentheses. If you forget to close the parentheses, you won't get the right answer. Everybody find the log button okay? I got 8.31. Try it. Make sure, if you have a calculator today, make sure you're getting 8.31.
So 0.92 to the 9.31 power.
So now we'll add 1 to both sides. And how many years is it going to take?
About 9 1/3.
9.3 years. Yep, that's exactly right. Now, that's only the first time we've ever done that. We're going to do it again tomorrow. Please don't panic. But when will this machine be worth half of its value? In 9.3 years. Randy.
So does log anything act as its own term?